Hey, have you ever looked at a massive crane hook, one lifting tons and tons of steel, and just wondered, how does that thing not snap? Or what about a simple gas cylinder? How does it contain all that incredible pressure? Well, it all comes down to these invisible forces playing out inside their very shapes. And today, we're going to dive deep into this fascinating world of mechanical stress.
So, really, how do they do it? How do these seemingly basic curves and cylinders, things we see every day, manage to control forces that could literally tear metal apart? That's the big question we're going to unravel right now. And to do that, we're going to focus on two perfect examples. First, that classic curved hook, built to handle just unbelievable tension despite its bend. And second, a pressurized cylinder, a container designed to fight off massive internal forces. Both of them rely on their specific geometry to survive.
Okay, but before we can really get how these shapes work their magic, we first need to learn the language of engineers. And at its heart, that language is all about one thing: stress.
To put it simply, mechanical stress is just the internal pushback of a material against an outside force. Think of it like this. When you pull on a rubber band, that feeling of it pulling back at you, that's a direct result of the internal stress inside the rubber, as all its molecules fight to hold on to each other.
Now, in something like a pressurized cylinder, stress isn't just one simple thing. Nope, it's actually acting in three different directions all at once. You've got hoop stress, which is trying to pull the cylinder walls apart, kind of like the metal hoops on an old wooden barrel. Then there's axial stress, trying to push the ends of the cylinder away from each other. And finally, you have radial stress, which pushes outward from the very center.
All right, here's where things get really interesting. You might think a cylinder is a cylinder, right? But in the world of engineering, a tiny change in its dimensions completely rewrites the physics of stress. So let's compare thin versus thick-walled cylinders. For thin-walled cylinders, think of a soda can. For those, engineers can get away with a really useful shortcut. They just assume the stress is spread out nice and evenly across the wall. But the moment that wall's thickness gets to be more than about 1/10 of the cylinder's diameter, everything changes. It's now thick-walled, and that simple assumption goes right out the window. The stress is anything but uniform. In those thin cylinders, there's a really neat rule of thumb. The hoop stress, the force trying to split the can down its side, is always exactly twice as strong as the axial stress that's trying to pop the top and bottom off. And you've seen the result of this. It's why a pressurized can will almost always burst open along its length, not across its ends.
Now, for thick walls, the math gets a lot more complicated. These are called Lamè's equations. But listen, don't worry about memorizing them. The only thing you need to see here is that the amount of stress now depends on that little letter R, your exact location inside the wall. The stress is no longer spread out evenly. It's actually at its highest right on the inner surface, and then it gets weaker as you move toward the outside.
Okay, let's pivot to our second case study. We're going to take a simple straight beam, the foundation of basically all construction, and see what happens to all those internal stresses the moment we add a curve. So in a standard, everyday, straight beam, everything is perfectly balanced. When you bend it, the top part gets squeezed together in compression, and the bottom part gets stretched out in tension. The stress builds in a perfectly straight line from the center, and right there in the middle, there's a line of zero stress. We call that the neutral axis. It's all very neat, very symmetrical.
But what happens when we throw all that perfect symmetry out the window and start with the curve from the very beginning, just like in our crane hook?
The second you add that curve, the whole game changes. The stress distribution is no longer a simple, straight line. It becomes what we call hyperbolic. It's uneven, it's asymmetrical, and, as you're about to see, the spot where the stress is highest has shifted a lot. And this brings us to probably the most important idea of this whole explainer. That curve creates a little hiding spot for stress, a concentration of forces that can cause big problems if you don't plan for it. And it all boils down to something called the neutral axis shift.
Okay, so this slide shows you the critical difference. The dashed line, that's our nice, predictable straight beam. The solid line is the curved beam. Now look closely. See how the neutral axis, that's the point of zero stress, marked N, has moved? It's no longer in the geometric center, G. It's actually been pulled inward toward the center of the curve.
So what's the big deal with this shift? Well, think about it for a second. The material on the inside of the curve, the concave side, is physically shorter than the material on the outside, but they're all part of the same solid object, so they have to bend together.
This means all that stretching and squeezing gets concentrated on that shorter inner surface. It becomes a stress hotspot.
And the source material puts it perfectly, saying that the stress concentration always happens on the inner or concave side of a curved beam. That right there, that's the danger zone that every engineer has to design for.
Now, here's the thing about engineers. They're incredibly clever. They don't look at this and see a problem, they see a design challenge. They don't try to fight this principle of physics, they use their understanding of it to build things that are even stronger.
So let's go all the way back to our crane hook. The person designing this knows, without a doubt, that the highest, most dangerous stress is going to be right there on that inner curve. So, how do you stop the hook from breaking at its most vulnerable spot?
Well, the solution is just brilliant. You fight asymmetry with more asymmetry. Instead of making the hook out of a simple rectangle or a circle, you design the cross-section so that it has more material, more bulk, on the inside curve. That extra material is there specifically to handle that concentrated load and helps balance everything out.
And these are the exact kinds of shapes that are perfect for the job. Things like trapezoids or T-sections are, by their very nature, heavier on one side. So by turning them so the thickest part faces the inner curve, engineers are basically putting more muscle right where the stress is trying to do the most damage. It's a way to distribute that load and make the whole thing much, much stronger.
And that's really the big takeaway here. Great engineering isn't about creating things with zero stress. That's impossible. It's about understanding exactly where stress wants to hide and then intelligently placing your material to manage it. It's about turning a potential point of failure into a core part of the design's strength.
It really makes you think, doesn't it? If something as ordinary as a curve is hiding this much physical complexity, what other invisible forces, what other brilliant design secrets are quietly at work shaping absolutely everything in the world around us?